Good day everyone and welcome to my YouTube channel and welcome to another episode of Visuals with Man. We are now at the second part of the video series celebrating the Mandelbrot set. By the end of this video lesson, we will be able to achieve these two learning objectives. Please pause the video and take a moment to have a look at each one. And now let's examine the mathematical definition of Mandelbrot Lemniscates. When we group points according to their escape count, they form distinct colored bands, and then tracing the precise boundaries separating these bands yields curves called lemniscates. So for a fixed iteration level n, these curves are described by the magnitude of z sub n of c is equal to r max, or maximum radius, where maximum radius is equal to 2. Alright, so this marks the boundary where the iteration stops, and we find the parameter c, or the complex numbers c, for which z sub n of c lies exactly at this threshold. So we use the recurrence relation z sub n plus 1 is equal to z sub n squared plus c. And as n increases, the lemniscates become increasingly intricate and approach the boundary of the Mandelbrot set. We built an interactive Plotly app which shows how these mathematical curves are drawn on the computer screen. The app scans the screen and finds all the pixel coordinates, or complex numbers, where the step-by-step loop hits the escape limit, the threshold of approximately equal to 2. At level 2, or z sub 2, the app finds 3098 boundary pixels, where the calculation reaches the limit right on the second step. At level 3, or z sub 3, the app finds 1694 boundary pixels that hit the limit on the third step. And here's the lemniscate curve at level 4. And here's the lemniscate curve at level 5. And at higher levels, the app continues scanning for subsequent iterations to map out the full boundary structure. Go ahead and run the Python script and see the shapes form live. To see these concepts in action, let us look again at how they manifest visually. So here on the left, we have the Python-generated lemniscate curve of L5 of C, featuring the algebraic roots highlighted in yellow. We got this by finding the roots of the lemniscate polynomial of L5 of C. And having these roots, we reveal the core centers that shape the loop. And here on the right, we just have the multi-level view. This concept of Mandelbrot Lemniscates serves as a powerful application and visualization of higher degree polynomial curves. And now let's examine the algebraic narrative and the underlying algorithm driving this construction. Right, so the process follows a strict recursive pattern where the new level, like L sub 3 here, is built by referring to the previous level's expression, square it, and then plus c. Like for example here at level 3, so the previous level expression is c squared plus c, so we have this one here. We square it and then we add c. So that's for level 3. So we got this recursive pattern here, and this recursive structure allows us to construct increasingly complicated polynomial expressions. Indeed, we are seamlessly bridging basic algebra with the complex dynamics of the Mandelbrot set. Let's bridge classical geometry with modern fractal boundaries by exploring Cassini ovals. So the Cassini oval is defined as the locus where the product of the distances to two foci is constant. So these curves exhibit three shapes. So when A is equal to B, we have the Bernoulli lemniscate. And when B is greater than A, they form into a one oval shape. And when B is less than A, they separate to two distinct groups. A here is the distance from the origin to any of the two focus, and B is a constant value which represents the square root of the product of the distances of a point, of any point along the curve to the two fixed foci. This beautiful geometric behavior provides a powerful bridge connecting classical analytic geometry to modern fractal boundaries. Let's compare the L2 Cassini oval with the limiting behavior of the Mandelbrot Lemniscates as n approaches to infinity. Alright, so on the left we see here the verification of the L2 Cassini oval where B is greater than A, forming a smooth oval shape. On the right we observe the Mandelbrot set limit. This is from Wolfram, so I encourage all global math and computer science enthusiasts to share the Python code or equivalent implementation to generate this figure. Now let's examine how computational methods allow us to estimate the area of the Mandelbrot set. We have the Monte Carlo Random Sampling, so we estimate the area of the irregular shapes by generating random coordinates within the bounding box. And then we multiply the area of that box by the ratio of the successful points denoted by M, those inside the Mandelbrot set, to the total sample size denoted by n. And now let's review law of large numbers. So this states that as the sample size increases, the experimental averages approach the expected value. We have the concept statistical convergence. This is the steady stabilization of estimated results into a precise, reliable final value. Alright, so check out the links to the companion videos for Monte Carlo, Lemniscates, and Cassini Ovals in the description below. Running the Python script multiple times for each sample size reveals how precision scales. Having a sample size of 100,000 would mean higher variance compared to an experiment with a sample size of 1 million. And because repeated large-scale runs demand heavy computation, this task serves an ideal test for hardware benchmarking and software benchmarking. So this figure here is the statistical estimate of Mitchell 2001 cited by Wolfram. And now let's have some philosophical and real-world implications. As you can see, our Mandelbrot set can be bounded indeed, right, in a box, okay, in a complex plane. However, it reveals endless detail in infinite zoom. Alright, so these principles are also reflected in art, nature, and mathematics, like in Celtic art that we can find in Lindisfarne Gospels. So I would encourage everyone to read the teacher research literature linked in the description below. Thank you for watching, and I will see you in the next video of the series celebrating the Mandelbrot set. Bye for now!